piston cylinder assembly containing 0.9 kg of air at a temperature of 300 Kelvin and a pressure of 1 bar. The air is compressed to a state where the temperature is 470 and the pressure is 6 bars. During decompression, there is a heat transfer from air to the surrounding equal to 20 kJ. Using the ideal gas model of air, determine the work during the process in kilojoule. So let me sketch a problem first. Okay, here we have a piston cylinder assembly, and then we have 0.9 kilograms of air in there. It's a closed system, but the piston is movable, of course. And the initials, like T1, the initial condition, the temperature is 300 Kelvin, pressure is 1 bar. It will be compressed, right? So meaning the system will do work to your no, the surrounding will do work to your system, will push the air inside so that is supposed to increase. T2 is now 470 Kelvin, and P2, the pressure now increased to 6 bar. So of course we know that if it will be compressed, the volume will of course change also, right? And during that process, according to here, during the compression, heat is transferred from the air to the surrounding equal to 20 kilojoule, meaning heat is being uh, transferred from the air to the surroundings, meaning heat leaks out because the, the temperature of the air inside is quite high already, so it leaks out also by heat transfer to the surrounding at a rate of with a value of 20 kilojoule. Meaning heat is being removed from your system. Now the question is, calculate work. Okay, so supposed to be for this one, we could just have work equal to the negative integral of PdV. However, sad to say, during this process, we don't know how does the pressure vary with volume. We are not given any idea of that. We're just given the initial temperature, the pressure, and the final temp and P, also with the Q, but we don't know really how does the process go being done. So we cannot use this approach as of the moment, so X muna. So let's try to work out with other approaches. So let's try to just remember the first law. Delta U is equal to Q plus W. Okay, and then since here we know Q already, we know Q to be negative 20, right? So that's fair enough. We know Q, so Q is not a problem. Work is the one we're looking for. So it's if we cannot solve directly for work, maybe we could solve for delta U first, right? If we could solve for delta U, perhaps then we can evaluate what is work. And how do you evaluate delta U? For an ideal gas, delta U will just simply be um, a function of the temperature. And in this case, we can just always use this equation for an ideal gas. Delta U is just equal to the integral of Cv, uh, Cv dt, okay? Cv dt from T1 of course to T2. And in this case, if we assume air to be an ideal gas, since air is just made up of N2 and O2, right? N2 and O2. We could just more or less use the Cv for a polyatomic or diatomic gases. Cv for that is just equal to Cv for diatomic gases is equal to 3 halves. 3 halves are, right? 3 halves are. I think I'm mistaken. This 3 halves are is for monoatomic since N2 is di, like N and N combined together. So we'll have here actually for Cv for ideal gas, which is diatomic or polyatomic, is 5 halves R, where R is the universal gas constant. Okay? So in this case, well, this will then be equal to, well, let's try to have that. And this is a constant, right? 5 Cv is, assume here that Cv is a constant, will not be a function of temperature. In that case, we'll have 5 halves R times T2 minus T1. Okay? This will just be equal to that. And what's T2 minus T1? Well, it's 470 minus 300. And what is R? Well, we could use R to be equal to 8.3145, okay, joule per mole Kelvin, right? I am using this value. So 8.3145 joule per mole Kelvin times ano nga yung delta T? T2 minus T1, that's 470. 470 minus 300. That's equal to what? 470 minus 300. It's equal to 170 Kelvin, okay? And therefore, this will give us times 5 divided 2 times 8.3145. This gives us 3533.67.7 joule per mole. Okay, joule per mole. First, we are not really have what we have obtained really is not delta U, but more or less molar internal energy change per mole. And if we would like to compute the actual delta U, maybe I'll write here as small u. But we just don't need to really be, just take a look, be focused on the units that you will see if, is it really the delta U or is it the molar delta U, meaning per mole. So since in this case we are given that we have 0.9 kilograms of air, so we are given with that, we can actually convert that how many moles will that be, okay? So to compute for the actual delta U, we'll just have N multiply it by number of moles, right? So how many moles of that? So we'll have here 0.9, okay, times roughly N will be in value nasa 28.87, or let me show that here. Air is approximately O2 niyan is 21%, okay, and N2 niyan is roughly 79, and this will be so 0.21, okay, 21%, 79%. O2 is 32, yung molecular weight. So yung N2 will be 14, that will be 28. So yung average nila will be 32 times 0.21 plus 28 times 0.79. It will be 28.8. Or actually you can use 29. Or I'm just using here 28.8 gram per mole. Okay, or gram per mole, but in terms, since this is not in terms of, we're given here zero point 0.9 kilograms, so we'll have here in terms of kilogram, this will be more or less how do I do that? I just convert this zero point 0.9 kilogram into grams, right? So I'll have the, wait, I convert this is in kilogram, I convert that to 1000 gram is to 1 kilogram, and then I convert this to moles. How many moles will that be? Well, 28.8 gram is 1 mole of your air. So moles of air first. I'm calculating first for moles of air, not in terms of kilogram first. So that will give me 0.9 times 1000 divide 28.8 gives me 31.25 moles, and therefore delta U in this case, I'm writing that here, will be 31.25 moles of air times 3533.7 joule per mole. Therefore delta U will just be equal to 3533.7. That will give me 110,428 joule, but since I'm using kilojoule, that will just be 110.4 kilojoule. Okay, and therefore from back to our original equation, one can then solve again what will be W, right? So from here back, how do you compute for work? Work will just be equal to delta U minus Q, where delta U now is known to be 110.4 kilojoule. Q will be what? Well, Q will be negative 20. Why negative? Because it's being released to the surrounding, negative 20 kilojoule. And therefore, that will then give us 110.4 plus 20 will give us 130.4 kilojoule. Okay, that's the work done by the process. Okay, so work here is positive because this the air in here is being pushed by the piston, or the surrounding is doing the one doing the work to the air. That's it. Thank you.